Hi everyone, and thank you for joining us today for our webinar, Understanding Industrial Acoustics, a Sound Strategy. My name is Kim Melton, and I'm going to be the moderator for today's presentation, and joining me are Doug Fast from Johns Manville and Pascal Everton from SLR Consulting. So before our hosts introduce themselves, I would like to go over a few logistics. First is that we're going to conclude the webinar with a live Q&A session. So if you have any questions throughout the presentation, you can submit them via the Q&A box on the right side of your screen. Now, if you don't see the Q&A box on the right side of your screen, simply click the Q&A in the top right corner. So also, we're frequently asked whether or not we send out these presentations upon their conclusion. And while we don't actually send out the presentation itself, we do post a recording of it online for you to watch at your leisure. So you can share that with your colleagues or come back and view it a second time if you think you'd like to do that. And this ensures that you can actually have the presentation within its full context. So this is also part of how we deliver the JM experience to you. So at Johns Manville, the JM experience is really a part of our culture, and it's based on 4 pillars: people, passion, perform, and protect. And we offer these webinars to help educate the market and offer a tool or a resource for you and your business. So we're continuously striving to improve and evolve these webinars. And if you have any comments or suggestions as to how we can better accomplish that, or even if you feel like we've missed the mark today, we'd encourage you to fill out the survey and that you'll receive at the end of the webinar, and you can offer your feedback on how you think we can improve or if we've met your expectations. So on that note, let's get to some introductions. Our first host is Doug Fast, and he's a senior research engineer here at Johns Manville. Doug, can you take a couple minutes to introduce yourself?
Yeah, thank you, Kim. As Kim said, I've been with Johns Manville for 20 years, and in that time I've spent about half of my career here in product testing and a large percentage in installation technical services. Also, I've done some work with single-ply roofing, and that's given me a large body of knowledge to work from and opportunities to work with a lot of different products and applications. Joining me today is Pascal Everton, and I'll let him tell you a little bit about himself.
Yeah, thanks, Doug. So my name is Pascal Everton. I'm from SLR Consulting. I'm a principal engineer with the company, and I manage the acoustics discipline in the Canadian part of the business. My educational background is electrical engineering. I'm a registered professional engineer and also a member of the Institute of Noise Control Engineering. I've been in consulting for over 15 years now, and I've worked in everything from architectural and building acoustics as well as industrial acoustics. So I've got a lot of experience with diagnostic field measurements of various types of equipment and computer noise modeling and noise control for large industrial facilities. So a little bit about my company, SLR. We're an environmental consulting company and advisory services with roots originally from the UK. And we've grown quite significantly. We're now a global company that spans across 5 regions with over 70 offices and over 1,100 staff globally. Primarily, we serve 6 industry sectors that we break up into built environment, infrastructure, power, oil and gas, and industry, as well as mining. And as a company, we offer over 30 technical disciplines and things such as air quality, wildlife, wetlands assessments, remediation, reclamation, and of course acoustics and so on. So to begin with the presentation, let's talk a little bit about why we have a need for sound control in industrial settings. So typically there's 2 main reasons why a facility would want to look at sound control for the equipment on site. The first is to control the level of noise that's on site and to meet the occupational health and safety requirements applicable to the jurisdiction. Typically that limit is 85 dBA for an 8-hour exposure to the noise. Anything above 85 dBA requires you to wear hearing protection, although some company-specific safety programs might differ from that, where lower noise levels also still might require hearing protection. There's also a safety consideration, excuse me, to ensure that workers can be heard clearly when they're working on site, and that safety signals, if there's an emergency alarm or something like that, can be heard throughout the facility. So if there's too much ambient noise from the equipment operating and there's an emergency on site, they may not hear that signal. The second reason is to consider the off-site environmental noise. you may control the certain noise levels on site due to the occupational noise standards, but there's oftentimes sources like pipe racks and stacks and cooling towers and things like that that don't need noise control because personnel can't necessarily get close to them. So the 85 dBA limit isn't a concern, but the sources could be significant off-site noise sources. And off-site, there's often environmental noise protection laws, which also vary quite significantly between jurisdictions. But the levels are often set to avoid sleep disturbance at residences and also to just avoid general annoyance and maintain the quality of life for individuals living near a facility. So equipment vendors often include a noise level of about 85 dBA in their technical specifications. And the reason for that is, like I said earlier, the 85 dBA occupational health and safety requirement. So by having their equipment be at a level less than 85 dBA, that requirement is satisfied. The problem is that when you have multiple equipment side by side, say you have a pump that operates at 85 dBA, but you place 5 of those pumps side by side, the cumulative noise from all that the equipment now adds up to something that's greater than 85 dBA. So often designers might assume that the equipment by itself is less than 85 dBA, so it's not a concern for the employees. But again, when you add them all together, then you're over 85 dBA, and it can become an issue. So it's important to consider the overall plant when you're designing these. Okay, so we're going to take a few moments to talk about the fundamentals of sound and sound control to get a better understanding of how it all works. So sound is simply a pressure disturbance in a medium, and a vibrating object causes positive and negative pressure in the surrounding air as the object oscillates back and forth. And the pressures travel through the air and create sound waves. So the amplitude of a sound wave is related to the intensity of that pressure variation, and it's often perceived as, or it is perceived as loudness. So the greater the pressure variation, the louder the sound gets. And the frequency of a sound wave is related to that speed of that pressure variation, and it's perceived as pitch. So the faster the motion, then the higher the pitch, and the slower the motion, the lower the pitch. Now, earlier I talked about dBA. So sounds are measured in decibels and are abbreviated as dB. So the A in dBA stands for the A-weighted scale. And A-weighted simply means that it's the sound combined to an overall level and measured with a frequency response that's similar to human hearing. So dBA is commonly used in measurements and regulations because it corresponds to how humans perceive sound. So here we see examples of sound waves where the longer wavelengths with fewer repetitions up at the top represent lower frequencies, and they're heard subjectively as a rumbling sound. Middle frequencies can be described as a kind of a roar, and higher frequencies sound more like a hiss. Frequencies often get grouped together into either third octave bands or full octave bands, and at the bottom of the slide there you can see the full octave band center frequencies. The unit of measure for the frequency is hertz, which basically just describes the number of repetitions of a cycle in the wave for every second. So this is just a chart showing some common industrial equipment with the range of typical frequencies that you can expect for each. So at the bottom we see structure-borne vibration at the very low frequency range, and then train engines and turbine exhaust have very low frequency content. Then aerial coolers are more in the low to mid frequency range, followed by pumps and motors, which are more into the mid frequency range. And compressors and piping noise tend to have a lot higher frequencies. And then finally, flow noise and valves are in a much higher frequency range. So in terms of noise control, sound absorption is useful to reduce noise levels. And we often use sound absorption. It refers to the amount of noise that gets dissipated by a material. So it's the ability for a material to dissipate the noise of the sound that's impacted onto the material. And it refers to how much sound actually gets reflected when the sound wave strikes the surface. It typically ranges from 0 to 1, where a sound absorption coefficient of 0 means that all the sound that strikes the material is completely reflected off of it, whereas the opposite, where sound absorption coefficient of 1 means that all the sound gets absorbed and none would get reflected. So in theory, it's possible to have, it isn't possible, sorry, to have an absorption coefficient greater than 1, because that would mean that more than 100% of the sound gets absorbed. But in practice, absorption coefficients greater than 1 sometimes are measured, and that's just sort of an anomaly in the measurement procedures used and the surface area of the measurement. In labs, the absorption coefficient of material are measured according to the ASTM standard C423. And it's measured by the decay of sound inside a reverberation test chamber while the room is empty, and it's measured again while a surface or an area of the material is placed inside the test room. And if you can just back up one slide there, Doug. Thanks. Along the bottom there, you can see the sound absorption coefficients for a typical material, and it varies as a function of the frequency for the given material. So some materials are designed for high absorption at lower frequencies, while others perform better at higher frequencies. But in general, most materials will absorb high frequency sounds more readily at low frequency sounds, or sorry, at high frequency sounds instead of low frequency sounds. So I just want to go over two physical principles that often get mixed up, sound transmission and sound absorption. So we've just gone over the meaning of sound absorption, which relates to how much sound gets absorbed versus how much is reflected when a sound wave strikes the surface. Sound transmission relates to the amount of sound that passes through an element or a given system. And the two are sort of related, but mostly they can work together to increase the overall effectiveness of a system. A material that's highly absorptive won't necessarily be effective at reducing the transmitted sound through it, and vice versa. The material that blocks sound transmission will not necessarily be very good at sound absorption. Actually, the opposite is normally true, because materials that are designed for high frequency absorption are usually thick, porous, and fibrous materials like fiberglass or mineral wool. And since they're quite porous, they allow sound to actually pass through them fairly easily. You wouldn't normally see a wall being built just out of fiberglass, for example. On the other hand, materials that are designed to reduce sound transmission through them, sometimes called transmission loss, those materials are very heavy and have internal damping. So since the material is heavy, its surface is often very hard. For example, if we say concrete, so while concrete is very effective at blocking sound, it doesn't do a very good job absorbing sound. So in theory, the ability for a material to block sound passing through it is defined as the mass law. And the formula is shown on the slide. It indicates that for every doubling of mass, the transmission loss through the material increases by 6 dB. Also, for a given mass of a material, the transmission loss of the material increases 6 dB per octave. So to put this all into context, we look at the example of a standard pipe lagging system. So the number 1 on the figure shows the bare pipe, which is our noise source that we're trying to mitigate in this case. Number 2 points to an absorptive layer, which allows the sound to be absorbed in the space, and it also decouples the vibration energy from the pipe from being transferred to the outer layer. Number 3 is a damping layer, which often mass-loaded vinyl is used for the purpose, as it adds mass to the overall system, and being a limp material, it prevents the cladding from resonating as well. And then the outer layer, number 4, is the cladding, which acts as a barrier to reduce the amount of sound that's transmitted through. And the different configurations and additional layers of materials can be configured to achieve different levels of noise reduction from certain lagging systems. So I wanted to touch on two terms that often get confused as well. That's insertion loss and transmission loss. Both terms refer to the sound level reduction as sound passes through a material or assembly, but the insertion loss is measured as the difference in sound level from a noise source with and without the treatment in place. So the sound level is first measured without any treatment, and then the treatment is, quote unquote, inserted, or hence the name insertion loss. You add the treatment, and then the sound level is again measured with the treatment in place. So the difference between those levels is the insertion loss of adding the treatment to your source. Transmission loss is the decrease of sound power through an element. And it's actually it's measured by placing a noise source on one side of an element or an assembly. And measurements are then made on both sides of the element to determine the reduction through the element. So you take the sound level on one side where you generate noise, and then you go on to the other side, take another measurement, and it's the difference between those two that gives you the reduction through the element. And the results, they're often rated as a single number rating known as STC, which stands for Sound Transmission Class. Okay, I'll hand it over to Doug now, who's going to talk about material characteristics influencing sound absorption.
Thank you, Pascal. As Pascal described earlier, when we do sound absorption testing, what we're trying to do is see how the product performs in an extreme environment. And we'll talk a little bit about what that testing looks like in some slides later on. But to start with, if you look at this table that we have here, we have something that's very hard and smooth, which is marble, which is our first one. And as Pascal described, this is almost a perfectly reflective type of material. You can see these absorption coefficients. Really, for the most part, at least 98% of the sound is reflected as it hits the surface. Now, interestingly enough, if you look at the concrete block just right below it, the numbers actually they're much higher, particularly at lower frequencies, but again, performance actually tends to decrease as you increase in frequency. And that's most likely due to concrete block being a little more porous, having little cavities that sound can reflect on and also and be absorbed more readily than a smooth surface like the marble that we saw in our first example. Kind of going back down to the mineral wool portion of this, two things to look at. We have two different mineral wool products, and they're both the same thickness but different densities. And the thing to note, and again, Pascal had already described that numbers over 1, they don't happen in the real world. This is really more of an artifact of the measuring system that's used to get this information. But notice you'll see that you have really improved absorption in the 250 and 500 hertz categories with the higher density than you do with the other one. But as you get in the higher frequencies, again, you see that the absorption is more or less the same. 400ths of an absorption coefficient is something you can barely measure and something you're not going to be able to hear. And then the final part of this is we look at, if you compare the third item with the fifth item, again, note that they have the same density, but there's a change in thickness. And note that you get a bump in performance, particularly at the lower frequencies at 125, 250, and 500 hertz. You can see that we have quite a bit of an improvement over what we have with the third item that's a thinner product. So again, as we increase thickness and density, we tend to get better sound absorption performance. This is a visual representation, and Pascal had touched on this a little bit earlier. One of the things that makes for a good sound absorber is, if you're using a fibrous material, something like a fiber diameter has a large impact. Fiberglass, and depending on the application, most glasses that are seen in building and industrial types of applications will have a kind of a standard fiber diameter. However, if you have something like an aerospace insulation that has a much smaller fiber diameter, you'll get better absorption at a given thickness than you will with something that has a larger fiber. And again, we already talked about bulk density, and certainly the denser the product that we have, the better it absorbs sound up to a point, and we'll look at that a little bit later too. And then also material thickness, and we saw just a small example there of just increasing the material 1/2 of an inch gave us really not a lot of benefit at the higher frequencies, but we got quite a bit of benefit at the lower frequencies. If you remember, Pascal talked a while back about frequencies and the cycles per second. Generally, the thicker the product that we get, the more sound is attenuated as you think about it wiggling through this matrix. It baffles it more effectively or dampens it more effectively. Now, kind of going to the image on the lower right-hand portion of the screen, if you're using something like a cellular product or an open cell foam, porosity has a lot to do with it. So if you have a lot of cells that sound can actually get into and reflect off of and have that sound dissipated as it hits those, that's ideal. If you have something that's a closed cell, it tends to act more reflective and will bounce off of that because there's no way that air can get in there and be dissipated or damped. And again, material thickness has a huge impact on this. In fact, there are some test methods within the one that Pascal had mentioned where you can take a material and put it directly onto the floor. You can get a measurement. If you just even create a half-inch airspace behind that material, you can actually increase the performance of the product. That's more of a function of how the product is applied rather than the material itself. Now, how we use sound absorptive materials, there's a lot of different ways, but really what we're trying to do is we're trying to use absorption to reduce echoes and reverberation. If anybody's ever been in a room where there's a lot of echoes, it's very difficult to understand because the sound is coming to you, you're hearing it, but it's also being reflected, so you're hearing it a second time, and everything's a little bit off, so it makes intelligibility difficult. Another thing you can do is, and as Pascal had described with insertion locks, you can put something around your sound source to help reduce the actual sound that gets into that interior environment. So one way is to actually control the echoes in the environment and then also try and manage the sound source so that we're having less sound getting into the environment in the first place. And as an honorable mention, this presentation is geared more towards industrial types of applications, but again, HVAC systems can also benefit from sound control treatments, whether it's a duct liner on the inside of the duct to help reduce sound as it travels through the duct, or to wrap around the outside of the duct to help reduce the sound that can actually break out into the environment or environmental noise getting into the duct and being transmitted down the duct. So that's another application. And then finally, and I think this is the one that most commercial and residential people are familiar with, is using insulation within a cavity of a wall to help reduce the sound transmission as sound goes through that wall. And there's some details along with that. It's more of a system, and as Pascal had mentioned, there's STC ratings that allow you to compare wood frame walls versus a concrete wall. And again, beyond the scope of this conversation, but just to let you know that those do exist. With that, I'm going to turn this back over to Pascal, who's going to tell us a little bit more about applications and other ways to manage sound.
Thanks, Doug. So, as Doug mentioned, the absorptive materials placed inside enclosed rooms help reduce the reflections in that room. So here's just two diagrams, the upper one showing an untreated room where you don't have any absorption or very little absorption inside an enclosed room. So the sound level near a source would be very similar to the sound level that's heard in the reverberant space far away from the source. Whereas if you add absorption to that room, so looking at the bottom diagram, the treated room, of course you'll still have some noise near that source, but as you get farther away from that source in the reverberant field, it gets a lot quieter. So this is a useful tool for mitigating noise in the reverberant field of a enclosed, say, for example, a building or some other enclosed space. On the next slide, you see the ratio between how much absorption is put into the room and a function of the decibel reduction in the room, or at least in a reverberant space. So if you look at number 2 is the absorption ratio, meaning you're doubling the amount of absorption in the room, you typically get about a 3 dB reduction of sound in that reverberant room. And then if you look at a 10-fold increase of absorption, you're looking at a 10 dB reduction of sound in the room. So it could be fairly effective, but once you have a lot of absorption already in the room, then you get a diminishing return on the amount of absorption that you add to the room. So obviously in industrial settings, equipment is not always inside rooms, so adding absorption to a room is not always feasible or the most effective way of dealing with sound, reducing sound. So oftentimes you want to look at reducing sound at the source, and here's just a table of different kinds of noise sources we encounter in industry and some possible noise control solutions. So equipment like pumps, compressors, blowers, motors, and things like that. Oftentimes you can get acoustical blankets that are fitted to go around that equipment, or you can put enclosures around it as well. And the enclosures could be either completely sealed, or there are removable enclosures as well that can be sort of put on with latches that are removable for maintenance purposes. For piping, oftentimes we will add pipe lagging around the length of the pipe. Another effective mitigation measure is to add a silencer near the equipment, and then anything downstream of the silencer will be much quieter. So it could be more cost effective to actually incorporate a silencer, which would reduce the amount of pipe lagging required. For aerial coolers and fans, this comes down to fan blade selection. Oftentimes fans are run very, very fast, and the way to reduce the noise from fans really is to slow down the speed of the fan. So by having a more efficient fan blade selected for it allows you to slow down the speed of the fan while still maintaining the cooling efficiency that's required. Or also incorporating VFDs or variable frequency drives allows you to slow down the fan when there's not as much demand for cooling, such as, for example, at nighttime when it gets cooler, you may be able to slow down the speed of the fans, and then it also reduces the sound level from the fans. Air intakes and exhausts, either from buildings and things like that, you can add silencers or acoustical louvers. And then just general noise from the plant, sort of the last resort, I would say, is barriers, because, of course, sound still travels over the barrier, and you often need very tall barriers in order to be effective. And then buildings, of course, are a way of controlling sound from an area, but can be very expensive, and then you get into all sorts of other requirements for ventilation and things like that as well. So here's a couple examples of some acoustical blankets. These are custom fitted and tailored to specific equipment pieces. So you'll have a designer come out to site, take very detailed measurements of the equipment that needs to be wrapped, and make a blanket that's custom fit for that. So it's very useful for situations where you need maintenance, you need access to the equipment underneath. The issue becomes once it's taken off, it becomes very difficult to put it back exactly the way it was put on the first time, and to ensure that your field personnel are actually putting it on correctly and making sure that all the little gaps and voids and things are all filled. So it's a good noise control measure, but it can be, if it's left off or not put on properly, then it's not as effective as it was originally intended. Here's some examples of pipe lagging. It looks very similar to your standard thermal pipe lagging, just that it's thicker and it looks like a bigger pipe, but really it could be a fairly small pipe underneath, and it's a fairly thick system over top. And just some examples on the left there, you've got an acoustical building. You can see that there's a number of acoustical silencers that are on the top of the building, as well as a large turbine exhaust silencer off to the side. And you can see that it's got its own support structure there. So these things are quite large and need to be accounted for early in the design stage. Because sometimes space requirements and things like that, if they're only thought of afterwards, you might be limited in what can actually be implemented. So it's important to look at these things early in the design. And then on the right, you can just see some silencers. It looks like a pipe going in on one side, and then it just sort of gets a bit thicker where the silencer portion is, and then goes back out to a standard pipe. So Doug's going to talk a little bit about the laboratory testing.
Okay. Thank you, Pascal. We talked a little bit earlier about the test method that was used to test for absorption and why we sometimes get some different results than what reality would tell us that we should have. What we do is this is an ASTM C423 sound test, and the advantage to this is we can test either a full-size material or even a finished product, something like an office panel. But what happens is we energize the room to what they call a pink noise spectrum, where all the frequencies are 100 decibels, all the way from 63 hertz all the way up to 8,000 hertz. And if you look at the image up on the upper right-hand corner, we leave it at that level and we turn the sound off, and then we measure how long it takes for that sound to decay down to the background level. And what we'll do is we'll do that with the room empty, and then we'll also put a sample in the room. We'll put it on the floor. The standard, I think, requires a 72 square foot sample that's placed on the floor, and then we'll do the same thing. We energize the room, we turn the sound off, and we measure how long it takes for that sound to decay back down to the background level. And from that, we put that into a formula, and out comes the NRC value, or out comes a coefficient. And then, as we saw in that earlier slide, we'll average 4 of those frequencies together to get the sound absorption, or the NRC value for that product. Now, the reason we get values that are over 1 is this test was developed in the early part of the 20th century. And what they did is they took the most absorbent material that they had at the time, which actually happened to be a horse felt type of board. It looked very much like a fiberglass board with maybe longer fibers, a little bit smoother. And that was the best absorbing product that they had at the time. And of course, over the years, with smaller fiber diameters and density and thicknesses, things like that, you can get values that are over that. And so that's the reason. It's rather than update the test method and all the materials that have already been tested, it's easier just to stick with what everybody knows. And we understand that if it's above 1, then effectively it is 1. Here's a picture of what that room looks like. A couple of things to note here. We have the diffusing vane on the top, which rotates as the sound is being turned on and turned off. And as soon as we turn the sound off, that microphone will start measuring how long it takes for that decay that we talked about. We have the specimen you can see here on the floor, and notice that it's a little bit cockeyed, so it's not sitting parallel with any of the walls in that room. And then also you can see between the floor and those rotating vanes, where there's also panels that are on that wall. And that sole purpose of all those panels is to make sure that sound field inside that room is as even as possible, so that the sound pressure level at the upper corner of that room is the same as it is down next to the floor. And so we're just trying to make this even field. And again, that microphone is rotating and taking measurements as it's cycling around to make sure we're getting a really good sampling rate to get good data. Now, what we do with this data is, we can take a look at it, and it's good for comparison purposes. Now, rather than go and cite every absorption coefficient at each frequency, we just use an NRC number, so it gives a good relative comparison, one number comparison, rather than something a little more complicated. Now, one of the things to note here is we saw earlier on one of the other slides that as we increase thickness, we can also increase that absorption coefficient. So one of the things to look at is if we start at the bottom, we have a thin blanket, and this is the blue line is Johns Manville's Insul-Thin microporous blanket. The red line is a silica aerogel blanket, and they're both 10 millimeters thick. And as you can see, performance-wise, they're pretty much comparable at the lower frequencies. Maybe Insul-Thin gives you a little bit better sound absorption at higher frequencies, but again, we're limited to thickness there. So 10 millimeters is about 1/2 of an inch. So now as we start looking at the red and blue lines that are just up from that, kind of in the middle, those represent 1.5 inches and 2 inches. And we looked at that in an earlier slide. And you can see that, once we get up to about 800 hertz, we generally match the higher density products, which are up at the top. But if you look at the 6 and the 4 inch products, which are represented by the green and purple line, you can see that those lower frequencies perform much better than they do, than the other products do. But maybe not so much once you get past that 800 hertz. It's all kind of about the same. So again, moral of the story is if you're really trying to get absorption, thickness is the easiest way to do it. So now we looked at thickness. Let's look a little bit here at density. And again, we have similar curves here. And the thing to note is if you look over on the left-hand side where you have the green and the red, which are represented by the 6-pound and the 1260 6-pound board and the 1280 8-pound board, you can see that their performance is actually better at those lower frequencies. It's translated above that lighter product, which is the 1240, which is a 4-pound density board. But again, once we get to that certain point, we see that the data kind of swerves and it's a little commingled. So, it's safe to say that above 800 hertz, everything is going to perform the same way at a given density. But if you need low frequency performance, density is another way to get there. So again, if we have something that's dense and something that's thick, that's going to be your optimal low frequency configuration. Here's something else, and I think it's something that Pascal and I see quite a bit, is a lot of times people will specify something that has a lot of absorption to it, and there's certainly nothing wrong with that, but then they'll put something over the top of that. In this case, we're looking at an example of R19 unfaced fiberglass insulation, and it has a facing on the top of it. So if we take the product without the facing and we run that sound absorption test, you can see we get a spectrum pretty much like what we've seen with the other samples. It's pretty much at 1 well, in this case, it looks like about 500 hertz and above. We're over 1. However, if you look at the FSK facing, and this would be either something like a metal building type of product or a bath that you're installing in a wall cavity, you can see that facing, as you get those higher frequencies, it tends to, the higher the frequency, the worse it performs, because that sound is reflecting off of that facing. Where at the lower frequencies, it's not so much noticeable because you have the thickness. Lower frequencies are a little bit easier to are dealt with by thickness, but higher frequencies, again, when they hit this product, they tend to reflect more, so it's not going to perform as well. Same would also happen with jacketing that you're going to have on pipes or any kind of facing you're going to have in a mineral wool type of or fiberglass type of insulation. Now, one of the things we talked about, and this goes back to what Pascal had talked about earlier, looking at lagging or insertion loss. And again, we start with a test where we start with a pipe. We run sound in that pipe. We take a measurement inside of this room, which you can see in the lower right-hand corner. Then we'll put insulation over the top of it, jacket it, and then turn the same sound on again and measure what that difference is. And essentially, we have our sound level with the bare pipe. We subtract the sound level with the lagged pipe, and from that we get insertion. We get a difference, for that particular frequency. And we'll look at some data here on the next slide. But what we've done is we had a request from a customer to get some of this information for our insulation. And what we did is we used an ASTM test method. It was E1222, and this is a standard test for measuring insulation systems on a 12-inch pipe. What we decided to do is we picked 4 common thicknesses that we had for our mineral 1200 pipe, and we used stucco embossed aluminum. Now, for the ISO 15665, they will specify a thickness and whether, like a steel jacketing at a given thickness. We tested stucco embossed aluminum because that's the product that's used in most cases. Again, uses a 12-inch pipe, and then we compared these results with the 15665 requirements. The result of that is that for the 4-inch thickness, did very well and met the A2 requirement in ISO 15665. The 1.5, 2-inch, and 3-inch products were close, and we'll see some of that data. But because we chose to use the thinner jacketing, that might have hurt us on this. But anyway, you'll see that we were really close to meeting. But again, performed very well. So just to kind of take a quick look, and won't get into too much detail here, but ISO 15665 is more of an application-based type of criteria. And they provide a certain performance level, what they call prescriptive performance level of how something needs to perform. So as an example, if you look up in the upper left-hand corner at the 1.5-inch thickness insulation, you can see that black line is, for the most part, above the red line. The red line represents the criteria that you have to meet, and the black line represents how our product actually performed. And what you can see is right around 500 hertz, we are slightly below that. So we're translated. So at that particular data point, we did not meet it. So we can't say that we meet that. However, certainly if we would use the heavier jacketing, it's safe to say that we could have met that. Also, if you look at 2 inches, kind of the same thing. The other thing to note is as you look at the thickness from 1.5 inches, 2 inches, 3 inches, and 4 inches, you can see that line starts to translate farther and farther away from that base case, and that's really just that thickness helping to dissipate more sound as it's going through increasingly thick insulation. So that's what we have for lab testing. I'm going to turn it over to Pascal. He can tell us about field testing and what they do in the real world.
Thanks, Doug. So, yeah, when we go out and measure in plant environments, sometimes we'll come across a large pipe rack like you can see in the picture there, and you can certainly identify that there's a loud source coming from it, but oftentimes we're too far away and or sort of not sure which pipe is the one that's causing the noise, or there might be multiple pipes causing the noise. So difficulty is we don't have a lab condition to go and test different types of pipes, and so we're in a noisy environment, and we need to be able to isolate these individual pipes and see what the contribution of noise is from each. So how do we do that in a plant environment? There's a few different ways. One of them is using sound intensity, which is basically a method that has 2 microphones that are facing each other. And Doug, if you just go to the next line, there's a picture there, a couple pictures of sound intensity, and so it's like I say, two microphones that are facing each other, and it measures the vector of sound coming in the direction that the microphone is pointed. So not only does it give you information about the amplitude or the loudness of the sound, but it also gives you the direction of the sound. So everything that is coming from behind can be removed from your sound measurement. The problem with that, just go back.
Right.
The problem with that is that it's very difficult to implement in the field. You have to set up a imaginary grid, and it can be done in practice, but it's quite intensive, quite labor intensive, and it requires a lot of measurement points, and can be difficult to employ. So SLR's developed what we call a pipe box, and essentially what it is a microphone that's inserted on one end of the box that you see there, that metal box. The side that's facing the pipe is an open-ended side of the box. So essentially what it is a little acoustical chamber with the microphone inside, and you've got a piece of the pipe that's radiating noise into the box. Sorry. So the box allows the outside noise or the other noise that's in the area to be protected from what's being measured inside the box, and allows us to get a fairly accurate level of what the pipe noise level is. So I'll pass it back over to Doug, who's going to talk about some insulation materials.
Okay. Thank you, Pascal. Now, here's some examples of how absorption can help an environment. And if you look on the left-hand image, you see we can see things that are draped on the ceiling, and certainly that's some sound-absorbing material. And again, sound-absorbing material in this situation could be just things like drapes or thin panels that are put in place to help reduce or attenuate that sound that's in that environment and help prevent it from being bounced and reflected back into this environment, which looks to be possibly a manufacturing type of situation. And again, if you look at the bottom center, it looks like a tube that might even have some kind of lagging on it to help prevent sound from escaping it. If you look over on the left-hand side, you'll see that we have some foam that's around a work area, and that piece of machinery in the foreground is probably what's making all the noise, but at least we're treating it at the source to help maybe prevent it from reflecting out into the rest of the workspace. I think one of the things that's important here whenever you're looking at applications is to always do your design work up front. Certainly, Pascal gets called out in the field to have to deal with something after it's already making too much noise. And again, it's always a good idea to think about what you're doing right up front and identify what those noise sources are and possible treatments. And again, I know Pascal can be quite helpful for doing that. Doing that, and certainly has a lot of information. Next, we'll talk about settling, sagging, and compression. Now, one of the challenges in an industrial environment is you have a high vibration, high traffic type of environment, and so this puts an additional load on the requirements for the insulation. Now, typically in a high traffic environment or something that requires a lot of durability, a rigid insulation makes a lot of sense. It tends to stand up well. The jacketing is very well supported, so it maintains its integrity. But in a high vibration environment, the thing that makes a rigid insulation work so well, actually acoustically, it makes it a poor choice, because you have because it is rigid, sound can readily conduct through that material as opposed to something that's soft or porous or spongy or open. A solution to that is to possibly use a composite system or a hybrid. Now, one of the problems that if you have a high temperature, high vibration environment with mineral wool or fiberglass is over time that binder that holds those fibers together can oxidize and become compromised and possibly cause that insulation to settle. And now you have less thickness to help reduce sound, so now you're actually conducting more sound through it. So maybe as an alternative, you could use something like a rigid insulation like a calcium silicate, which provides good base support, and then maybe use an outer layer of mineral wool so you get the vibration resistance of the calcium silicate, but then you have the outer portion, which is mineral wool, which will do a better job acoustically for you. Another option would be we have a thin blanket insulation, our Insulthin. Again, it's a heavier density product, and so it's going to help dampen sound very well, but also it has a great deal of temperature resistance, and so that's also going to function well in that type of environment. Now, one of the things we talked a little bit earlier about some test results, and here's a comparison of insertion loss of a few different products. So looking here, and we'll start at the bottom and work our way up, we see on that bottom line, or I guess it's mostly bottom on the right-hand side of the screen, that would be our 2-inch calcium silicate product, our Thermal 1200. And you can see at low frequencies, because it's heavy, it performs very well. In fact, better than mineral wool, down around 125 and maybe equivalent around 250 hertz. But again, as you start to increase in frequency, you can see the performance doesn't quite keep up with what it does with mineral wool. We talked earlier about different thicknesses and how they perform. That middle purple line is 1.5 inch thickness. And how that would perform. And then if we have a 4-inch thickness of mineral wool, you can see that there's a dramatic difference. And again, we talked about that shift on an earlier slide, and you can see how much more it's shifted. Another thing to note, too, is that as you go farther up in frequency, or you go from left to right, you can see we have a much larger gap, between all the different lines. So again, we're at almost 40 decibels that we're attenuating with the mineral wool at 4 inches at about 5,000 hertz, whereas we're about 30 with the 1.5 inch thickness, and we're down about 18 with calcium silicate. So pretty big difference. Okay. With that, I'll turn it over to Kim, who has some additional information and resources that are available to those of you on the phone.
Thanks, Doug. So as he said, I would like to take a few minutes to go over some of the additional free resources that we offer that you can actually use to help navigate things like sound control. So the first resource I'd like to discuss is our blog. Now, we both write and curate content for the blog. So this means we're not only relying on our own technical experts at JM, but actually sourcing information from technical experts throughout the industry. And this is to ensure that the content that we offer you is really well-rounded. So these blogs also hit on targeted technical information, the latest news in the industry, and scientific details that are actually critical to successful insulation system design and operation. We strive to make this content as rich and relevant as possible so that it can better serve you and the information that you need. Now, the second resource we have is our exclusive content portal. So as we know, you can't always attend our live webinars, or we record each of them and post them online in this exclusive content portal. Now, this is a library of both our recorded webinars, our videos, our white papers. So if you miss a webinar or there's anything that you're actually looking for, then we have additional detailed information on a specific topic that is in this area. So this is a great resource that you can rely on to dive into additional details. Now, finally, the 3E Plus tool that we have here that I'd like to talk about is actually, we've got a customized version that has information pertaining specifically to JM products. So while the standard NEMA 3E Plus tool is actually going to give you established approximated insulation thicknesses based on generic material performance specifications, the JM NEMA 3E Plus tool actually gives you thicknesses pertaining specifically to JM products. So if you know you're specifically going to use a JM product and you need to establish the thickness of the insulation for your application, this is a tool that you could download to do that. So also, next slide please, Doug. For everybody who attended the webinar, you will receive a certificate of completion following the webinar, and this will be sent directly to your email by Friday. So with that, I would like to go ahead and open it up to questions. Now our first question that came through, Pascal, this one's for you, and my question is it possible to predict the impact of multiple equipment classified at 85 dBA operating together?
Yeah, I guess the answer is yes, it is, if they truly are operating at 85 dBA. There's a couple things to consider there. There's the distance between them and the environment that they're in, and so you'll get different results. So theoretically, if you add two pieces of equipment that are 85 and you add them together, you'll get a 3 dB increase. So obviously 88 dBA. But like I say, it depends on the environment that they're in and the separation between them and a number of other factors. So I guess the simple answer is yes, but the real answer is it takes a little bit more work to try to figure that out.
All right, the next question is for you again, Pascal, and that is, what is the maximum flow velocity for noise control considerations?
Sorry, did you say the flow velocity?
That was the question, yes.
Yeah, there's no hard and fast number for that. It really depends. A lot of the noise is actually not generated from the flow inside the pipe. I assume that the person's talking about industrial applications. When it's different, the reason I say that, it's different when you're talking about HVAC applications. But for industrial applications, a lot of the noise is actually generated from the equipment that's attached to the pipe, and so you get the vibration that's transferred along the pipe casing. It's not so much the actual flow of the product that's inside the pipe that causes the noise.
Thanks, Pascal. So the next question we have is, how does temperature impact the structural integrity of an insulation, and does it still have acoustical performance if the structural integrity has been compromised?
Doug, do you want to address that one?
Yeah. Well, again, I always hate this answer, but it depends. If you have something that has been heated and maybe the binder's been oxidized, as long as it maintains its thickness, it's going to provide the same performance that it did before that happened. But if you have anything where that thickness is reduced, then that's going to have an impact. And as we saw in the differences in thickness, if you took a 4-inch thickness of something and it was compromised to just say it was settled down to 1.5 inches, you would see a reduction in performance, maybe somewhat similar to what we saw with the insertion loss, where you'd probably maintain a lot of that high frequency performance, but the lower frequencies would see more of an impact, or more of a lessening.
Thanks, Doug. So the next one is for you, Pascal, and that is, do you account for external noise while mapping noise levels, especially when external noise will be quieter compared to a day in an industrial area?
Sorry, can you repeat that? When you say external noise, I assume?
I understand,
I assume they mean off-site, but go ahead.
Yeah, it says, do you account for external noise while mapping noise levels? The gist of it.
Yeah, I think what they mean by external noise is noise levels off-site, like outside of the industrial facility. And the answer is yes. So we have computer noise models that predict the propagation of noise through the air due to dissipation and ground factors and other such things, and structures in the way and things like that. So yes, oftentimes, or the majority of the time, we'll be looking at larger areas that the sound from the facility will impact.
Thanks, Pascal. So this next one is for Doug, and that is, can NRC values be interpolated or extrapolated between thicknesses or densities? Not
really. the thing about acoustics is and I think I think we're used to doing additive things when we're talking about thermal performance. Acoustics it doesn't work that way. It's, as Pascal said in an earlier example, when you double the sound level of something, you don't take 85 and get 170 decibels, you get 88 decibels. So, it really needs to be measured. You can make an educated guess. It might not be too far off, but there's no real models to accurately predict that. It really needs to be tested, and quite honestly, testing's pretty quick and easy to do for those types of things.
So this one, Doug, is for you as well, and that is, have you experienced any issues with corrosion under your insulation materials? And I think that's specifically targeting the insulations that are used for acoustical control.
Oh, gosh, we have whole webinars based on that. Again, I think with any system, in order for it to perform properly, it needs to be kept clean and dry. Having said that, the corrosion properties really depend on the material that you're using. Certainly our calcium silicate and perlite products work very well for that. And again, as we saw in an example, if we had a high vibration type of situation, a hybrid system, I think, would probably work best. And our Insultem product has really good corrosion capabilities as well. So I don't know if that directly answers the question, but just very at a high level, you always want to keep that system as clean and dry and undamaged as possible for thermal and acoustical reasons. And
to further elaborate on that, Doug, as you mentioned, we do have about 3 webinars on this that you can find on our exclusive content portal on our website, and these go into really good detail about the types of materials that you can use to prevent corrosion under insulation. So the next one I have for you is for Pascal, and is there an easy way to explain to us what the difference in sound pressure, or what is the sound pressure loss via distance?
Excuse me, sorry, the sound pressure loss at the distance?
Yes.
Okay, so theory, the simple math is that you get, for assuming a point source, so a very concentrated single source, you'll get a 6 dB reduction for doubling of distance. But again, that's a very simple mathematical way of looking at it. When we run computer noise models, there's certain standards that exist, which talk about the propagation, and if there's barriers or structures in the way, or the ground absorption and the absorption from the air, reflections off of other surfaces and things like that. So there's a lot more to account for. But yes, the most simple math is to say that 6 dB per doubling of distance is to be expected.
Excellent, thank you. Doug, this one actually pertains to HVAC systems, so we may actually defer it to our HVAC experts, but I'm going to give you a crack at it. And that is, would you have a recommendation for ductwork that supplies a classroom where the air handler is just too close? It's difficult to replace with lined duct.
Well, okay, assuming that air handle is where the noise is coming from, the best thing you can do is add a lot of absorption to the inside of that duct, and I'm assuming it's just traveling straight down. And Pascal might have some insights into this, but if there's room to put an inline silencer or something like that, that would also be probably the best that you could hope for. The only other thing I can think of is if there's a way they can snake a longer run and maybe get a bend or two in it, which isn't good from an airflow standpoint, but at least you could it has more of an opportunity to dissipate that sound level that goes through the duct, because insertion loss with ducts is usually a decibel reduction per foot. I don't know, Pascal, do you have anything to add to that?
Yeah, I agree with everything you said. The only other measure might be to enclose the entire thing just with an additional enclosure around, so that you get less transmission. Of course, you get breakout through the duct, but if you have an additional enclosure around everything, then you reduce the sound level transmitted into the classroom.
Thank you, guys. So, Doug, the next one is for you, and that is there a significant difference in price between commercial and industrial sound material, and why?
Yeah, I'm not a pricing guy. I don't know. My understanding is that they're roughly at parity. and it's not like we have a, something secret and expensive that's in one industry versus the other. They're, as far as the basic materials goes, I think they're competitively priced within their markets. I don't know if that answers the question. I guess the shorter answer is I don't know those specifics, but we could get you in contact with somebody who could speak to that.
Thanks, Doug. So we have one final question here. It's a little vague. If you guys can interpret it, great. If not, we'll actually follow up with the person who asked it. And that is, have you tested a lead liner on a scale against mineral wool? I
can say that we haven't. I'm not sure what I guess I'm not sure what the intent would be, but if it's like from a pure transmission standpoint, like Pascal said earlier, there's mass law that you can calculate the weight per square foot, and so if you had a certain weight of lead and you had a corresponding weight of mineral wool, theoretically they should perform about the same. But I'm not sure what that question is. Any thoughts, Pascal?
No, I think I would interpret it the same way, other than that it would take a lot of mineral wool to match the weight of lead.
Yeah. Yep.
We actually had one final question come in, and Doug, you can speak to this pretty quickly, and that is, do you have any proprietary materials or system that is mainly mineral and calcium silicate for acoustics?
We do not. We don't have anything proprietary, but of course we offer both products, and we're the only North American manufacturer that does. So, yeah, we'd be happy to set you up with that too.
Excellent. Well, that's going to wrap this up for today, and that concludes our questions. So, as I mentioned at the beginning of the webinar, we do have a survey that's going to follow this, and we'd really appreciate it if you take a little time to offer your feedback. Now, additionally, if you have any questions that you were unable to ask, you can actually submit them via the survey, and we'll actually respond to you directly via email. And again, we're going to post a recording of this webinar on our exclusive content portal in the next few days. So if you've missed any part of the presentation, or you'd like to view it a second time, or even if you feel like the content could be useful for one of your colleagues, you'll be able to access it on our website in our exclusive content portal. So thank you very much for attending today. Doug and Pascal, thank you for your time as well. We hope you found the information useful and relevant, and if you have any questions, please don't hesitate to reach out to us directly or via the survey. So take care and enjoy the rest of your week.